Okay, I guess we can get started. My part in this today's meeting, I think, will be quite short. Two things on the agenda. One, I'm going to first I'll hand over to Jason, and he wants to talk about the new address range uh, design. This regards mostly PR 2961 if you want to load that. And I believe, and this is just because it was noted in the agenda, that it also concerns this fixed decode packet trace as well. Is that correct? That was, well, anyway. So I'll hand over to Jason.
Yeah, I don't know what 2844 has to do with this.
Oh, sorry, that was just
Partial
in the
to
agenda.
June.
There was some note.
But
Yeah, you can ignore that if there was an. I thought that was in the agenda. I just wrote it down kind of verbatim. Okay, did I disregard that? Maybe it was a typo. And then we'll move on to Mayar, who's going to present what he calls the gem5 orchestration package, which is well, I'll let him talk about it, but it should be interesting. So Jason, do you have slides you want to go through?
Yeah.
Okay, sure. I'll just stop sharing.
Looks like there was a typo in one of the numbers on the
Oh, okay. I couldn't figure out why that was relevant. I was just like, okay, I'll put it in.
It's supposed to be it was supposed to be the link to the PR and the link to the issue. I don't know what
Oh, I
happened.
see.
Okay, let me share. Can you see my tab? Can you guys see my screen?
Yeah, I can see your
Yeah.
your Google doc thing.
Cool. Okay, so what I want to do is talk a little bit about the changes to the address range that I pushed in the PR, which is not linked here. Sorry. The purpose of this is to let people know what's changing and to give background to help get this reviewed. It's a pretty big change. It has a few thousand lines of code changed. Sorry for that. But I want to do anything I can to try to make reviewing easier. So the reason for this change is that address range was very inflexible. Previously, address range, which is used throughout the code base for all the places where we might have one address range that is backed by multiple banks or multiple different physical devices. So when we're doing interleaving across, say, your LLC or interleaving across memory controllers, address ranges are used, and they're also used a lot of other places. So previously, the address ranges you could do interleaving across multiple devices, but only bitwise interleaving. So you could select bits to use, and you could select XOR bits to use, but that was it. So that meant you couldn't have a non-power of 2 number of memory controllers. So, a lot of devices today have like 12 memory controllers, and that was not possible to model in gem5. And the other thing that was missing is it was really difficult to set up a system that had a hole in the address range. So for instance, in x86, the physical address range runs from 0 to 3 gigabytes. There's a hole from 3 gigabytes to 4 gigabytes for IO, and then 4 gigabytes and up is your memory. And my understanding of what actual hardware does is they take that 3 to 4 gigabyte hole and remap it to the top of the address range or something like that. So we couldn't model that in gem5 either, which was causing issues for x86 full systems. So I set out to refactor the address range to solve these two problems. So now what we have is address range has a pointer to a policy, and that policy is what implements the interleaving policy between different channels. There's 2 policies implemented so far. One is the masked interleaving policy, which is basically just what was there before. And then the other one is the modulo interleaving policy, which does interleaving based on just a modulo number. So you can have 3, 12, 17 channels if you want to, and which channel you choose just based on the modulo. You can imagine more complex policies, but I haven't implemented any yet. And the Python API has also been extended. Any thoughts or questions so far? Okay. So then on top of these policies, to implement the sparse address range, I tried a couple of different designs, and I settled on this design as being the most straightforward. So the address range itself can be either sparse or not. And when it's sparse, it can have a set of address ranges for it. And then there's a conversion method from the logical address range, or the address in the address range to a actual logical address within the range. And so this code is more complicated. It does add some performance overhead, but that performance overhead is only there if you're using sparse address ranges. So this also allows you to combine sparse address ranges with other interleavings. So you can be sparse and also modulo interleaved, or sparse and mask interleaving. And the modulo and masked interleavings operate on the logical unsparse addresses, not the original sparse addresses. And then the other changes that are in this PR are abstract memory and physical memory were updated, mostly to support sparse address ranges. So it used to be that all the abstract memories that were sharing an address range would have one physical memory backing. Now it can have multiple physical memory backings to deal with the sparse address ranges. The x86 board has now been updated, so we don't have to have the 3 GB limit. Channel memory has been updated to support sparse interleaving. The channel memory still only supports masked interleaving by default, but you could add your own channel to memory for non-powers of 2. And then, of course, all the Python API is extended. And the other thing that's not listed here is I found an optimization in the physical memory where on every load and store, this was a function called is physical memory was called, and I optimized that function to get an overall like 2 to 5% performance improvement in gem5 overall when using Ruby in full system. So whatever overheads the changes to address range added, which were minimal to nothing, this optimization that I found definitely hides all that. So in conclusion, I really would appreciate people reviewing this PR so we can try to get it merged, and let me know if there's any feedback.
I have one quick question about how this will work with the TLM ports. Like, do you expect us to define it ourselves? Like, for example, for the TLM generic payload, are we supposed to, uh, you know, glue it on the TLM ports ourselves, or will it be still referring to this global mapping?
Sorry, can you repeat that? It's kind of hard to hear you.
Oh, is it better? Like, can you hear me okay?
Yeah, that's okay.
Okay. Yeah, so I'm thinking in terms of TLM 2.0 glue for this mapping. So earlier we used to assume systems global map for TLM. Like if we have TLM sockets working with gem5, we'll assume like a global system address map. With this change, do we expect to create additional ports in TLM to allow this policy?
Yeah. Okay. So nothing should change if you want to keep the same behavior. So this is fully backwards compatible with the behavior before. So out of the box, the behavior doesn't change in any way. If you wanted to have these TLM ports respond to different address ranges, so like say interleaving across the ports or something, this now just gives you more flexibility with the kinds of interleaving that you can do.
I see. Okay. Yeah. So same thing for DMI also. Like as you're saying, probably for as long as our legacy use case, nothing needs to be modified. But if we want to utilize additional interleaving, we'll have to make those changes. Correct?
Correct. Yeah.
Okay. Got it. Thank you.
Any other thoughts or questions? Yeah, Giacomo.
Yeah, so I mean, if I think if I understood correctly, I mean, sorry, I joined later. I think I see something that everybody was waiting, change everybody was waiting for. There is a question that maybe is related to the TLM one, which is I don't know if you recall the sort of backdoor implementation in gem5. Like, is that backdoor compatible?
Yeah, good question. So the backdoor is something that I didn't look much into because there was in the code there was a guard on the backdoor that said if the address range is interleaved, it doesn't support backdoor. So I don't. My understanding with that was that my changes won't be impacting the backdoor at all because the backdoor only supports non-interleaved addresses. I didn't test with the backdoor because I don't know if there's any public testing code which uses it. But I did test with KVM on x86, and KVM works with whatever kind of interleaved addresses are there.
I don't remember. Does KVM use the backdoor mechanism as well?
I don't think it does.
Right. I mean, it's probably like, again, like not a big deal, but it would be nice if we could add some, as you were mentioning, like some simple backdoor tests. So so that we make sure that every use case is not that there's a blocker for this contribution. It's just like in general, I think is like one of the things that I know it exists, but yeah, not particularly used by upstream folks, I feel.
Yeah, that's definitely true. If you have a pointer to even where in the code this would matter. So
Right.
I was looking at this code here. Pulling it up real fast. To me, the way I read that code is that if the address range is interleaved, the backdoor will never be used. But if there's an example of interleaving and backdoor, let me know and I can try to at least reason through whether this will work or not.
Well, so interleaving, I presume that interleaving is one of your main case. The question is, so is this PR also addressing sparse, not necessarily interleaved, but like sparse ranges where like you basically have like a abstract memory which is responding to sparse addresses? Because that would be a problem with the backdoor, for example, I feel. Because you basically provide a pointer to memory straight away, and if all of a sudden you don't have a contiguous chunk, but you have like two separate chunks, then you have a problem.
Yeah, let me, I think that check should probably be range interleaved or sparse there. I think I changed that at one point. I will fix this check. But yes, so the way the sparse interleaving work, or the sparse address ranges work, is that it provides the abstract memory with two different pointers to the backing store, which would not work with the backdoor. So let me, yes, I will make that update. Thanks.
Thanks.
And also, like you mentioned about some of your tests, will you be releasing those tests as well so that others can also try, or maybe some examples on how to, for example, X number of memory channels and how to add this whole address map? So some sort of example will be helpful.
Yeah, so the in the PR you can see the changes that I made. I don't have I'll push an example with the modulo interleaving.
That's a model.
Because that's the only one that's not in the PR. But for the sparse address ranges, I updated the channel memory to support sparse address ranges. So you can kind of look at that code to see how to use it.
Okay, got it. Thanks.
It's pretty straightforward. Yeah, it's relatively obvious. I also added improved documentation to the Python interfaces as well. Any other questions or thoughts on that?
Okay. Thanks, Jason. Now I'll hand over to Mayar, who's going to talk us through, I believe you call it the gem5 orchestration package. Yep. We can see how I use gem5. So
yeah. Okay. Cool. Thank you. Hi everyone. I'm Mayar. I'm here to show you guys some of the development that I've been doing on the side of my research, especially on how to use gem5 more efficiently using our infrastructure. So just as a disclaimer, this started as me trying to kind of organize my gem5 simulations a little bit more, and it kind of graduated toward basically a little bit of reinventing Slurm, but also like adding features that are probably specific to gem5 and probably like specific to doing research. So I mean, we all use gem5 and we use it for research, development, and basically the process starts by extending gem5. We might add a new hardware model and add new stats because we want to basically find insights. We get a bunch of different benchmarks. We build we build configurations consisting of different models, let's say, I don't know, an inclusive cache, an exclusive cache, things like that. We diversify the parameters, so it creates a big simulation space. Like, I don't know, usually for each project that I've had like, I don't know, upwards of 100 simulations for just one project. And then we let these things run, and then we get the stats, and then we look at the stats if they make sense or if they point to a new idea, new insight, or improvements that can be done. We basically repeat this whole process again. So when you take this into consideration, one project could potentially require upwards of 100 simulations, and then each simulation can require upwards of 10 gigabytes per simulation. I think I haven't ever had a full system simulation that required less than 10 gigabytes of like host memory. And then each full system simulation can take upwards of 5 days. Right now I have had jobs like that took 27 days, or like right now I'm running something that has taken 9 days and hasn't finished. And then there are bugs that we might introduce as users when we develop in gem5, or there are undefined behaviors such as KVM. So basically, using parallelism to kind of do these jobs in parallel, and basically some platform to work around this unreliability of the simulations is, I think, necessary for timeliness. So right now, I think in our lab we have, I think, upwards of like 500 cores of processing power and like I think 3 terabytes or something. I think maybe even 4 terabytes across multiple machines. So it, like at some point it becomes a very difficult job to kind of manually orchestrate all these jobs across all these machines. I know like the answer to this is probably Slurm, but yeah, we'll get to why I didn't use Slurm, and it's not at all technical. So I started developing this Python package that kind of allows me to orchestrate my jobs across all of our machines. So, and I started by defining classes. So 3 or maybe 4 main classes in this Python package are the class host that defines one machine that has a certain compute capacity, like it is defined by a domain, like kind of a URI, and then it has a connection that kind of allows remote procedure calls and serving files over basically serving files remotely. So basically, you can talk to this host, say launch this job. It'll launch that job. You can get its status, and then it'll also be able to serve files from that job. So let's say the sim out of your gem5 simulation or the sim of your gem5 simulation. And then I have this utilitarian class called experiment, which basically is a list of jobs. And then given a certain available capacity, it can give a candidate job to launch. And then I have the class job that is defined by basically a certain demand. So that is the compute demand. And again, these are basically broad terms and user defined. So demand and capacity kind of go hand in hand. It's kind of user defined. That's where probably like systems like Slurm are way better than this. And then it has a CWD, like a command and like a path to where the standard out and the standard error of the job have to be, and a list of auxiliary IO. So for example, in gem5, we have the stats file that is another file that the gem5 writes to, and we might be able to, we might need to kind of observe it as it forms because we might dump multiple times into it. Any questions so far? Okay, awesome. So, and then I have the scheduler class that is basically the center of all this. It takes in a list of experiments and hosts and launches 3 threads. One is a console, which is the user IO. We can add new experiments and add new hosts, take away hosts, delete experiments, upgrade hosts. I don't know, like if someone else is running something on my host, because my capacity is user defined, I can go look at the host, and if they are done running things, I can upgrade the host to say, oh, this is their capacity. If someone wants to do something on the host, I can reduce the capacity of a host. Then there's the thread that does the actual scheduling. You know, it looks at the experiments, at the hosts, what their current states are, and launches the jobs. And then another thread that basically plots or like visualizes everything that is going on. In the scheduler, like what jobs are running, other things. So a little bit of like a demo, this is, yeah. So this is the kind of script that you have to write. I do not, okay, can you guys see my cursor, or do I have to use a, can someone tell me?
Your cursor.
Okay, yeah. So basically in this script that I will pass to the scheduler, I will define hosts and experiments does not have to have both, like, and I can do this in increments. So I'm defining a host called Cascade, like I'm giving it the name Cascade, and then that's the URI. Probably shouldn't have had it here publicly anyway, but and then these are 2 port numbers that my scheduler will use to talk to this host. Port 9300 is for launching jobs, and then 9301 is for serving files. And then I have an experiment, which is of the class gem5 experiment, which itself inherits from experiment. I'm giving it the name test. So this is the CWD of that experiment. Then every gem5 experiment uses the same gem5 binary under this path. Then it also has, like, gem5 experiment also has a base output directory where the basically M5 outs of every job in the experiment will be put in that directory. So I can add a job to this experiment by calling register job. I'm adding one gem5fs simulation to test experiment. I'm saying that this job has a demand of 1. Notice how Cascade has a capacity of 2. So basically, potentially, I can have 2 of these things running at the same time. This is the path to the run script that, like, relaunches the job for it. And this is the path to, like, the checkpoint that it's restoring in this specific job, and other inputs to this. So basically, gem5fs simulation is a wrapper for the class job that initializes all those CWD commands, standard out and standard error, for the class to be used. And then, like, in the terminal, like on Cascade, there's, like, the downside of this package is that there's a little bit of a downside here where I have to go manually launch these these worker units and say, hey, this is part of the package. So here I'm saying helper work, and this is the port 9300 that you have to work on or kind of listen on for remote procedure calls, and 9301 for serving files. And then in that config script, it was basically in accordance with this. And then here I launch a scheduler saying that, like, basically show your dashboard on port 9400 and, like, pull every host every 2 seconds. So, and it gives me a console here for me to kind of launch my jobs. So any questions so far? Awesome. Let me now show you guys a different okay. Is this the okay, yeah. Okay. Sorry. Okay. I guess. Okay. Okay, so before I came to this meeting, I basically launched this just to check things. So I basically typed into the console process t.py. T.py is the path to the Python script that defined all the hosts, and it all defines all the hosts or the experiments that I need to launch. Like, I can run another process. I don't know. This does not have path intelligence yet. I haven't been able to probably not a good idea to run this again. So I won't. But so the console looks like this. So you have these commands, process, list, kill, capacity, and stop. So process is for processing a Python script. And list basically lists all the hosts or the experiments that are that the scheduler is using. Kill can kill an experiment or a host. So basically, when you kill a host, it'll wait for the host to finish. It'll stop scheduling new jobs on the host, and it'll wait for the host to finish all its running jobs. And then on the worker side, you don't have to do anything. So, and now to show you the dashboard for it. I need to find the here, not here, not here. Oh. And so here's the dashboard running for that one scheduler. What happened here? Yeah. Oh, yeah, this one. Sorry. Okay, yeah. So basically here you can see, oh, this is the job from experiment test that is running on the host cascade. The status for it is running. And like if I want, I can look at the standard out of that one job or the standard error. It'll update every now and then. Even the terminal and the stats, I mean, right now it's empty because simulation hasn't dumped anything. And yeah, and if I want, I can just send a kill signal to the running job, because I might at some point notice that, oh, I made a mistake because I saw it somewhere else. This is going to fail. So I might as well just kill it now. So if I kill it now, it'll take some time for it to be killed. And now I can basically, let's say I go ahead and fix the bug, and I can just say reset, and it'll reset launching the job, and it goes back to running on that host. So these are basically the features that I wanted to have when I was launching all these simulations across multiple machines, and I basically built them for myself. Any questions?
I have a couple. If else. So I'm really sorry if you went over this. There was a part of your talk I was a little bit distracted by an email, but could you just remind me again, like why wasn't Slurm a good thing for this? Like what was the exact reason?
So this didn't start as an alternative to Slurm. It was started as me basically trying to automate like generating command lines for myself.
Yeah.
And then it kind of then graduated toward that. And like the scheduling logic did not seem as difficult as it ended up being. So instead of learning Slurm, I decided to build my own thing.
Okay.
This, however, should be compatible with like porting it to Slurm, or like the classes, like the job class is still useful for like generating the command line if someone wants to use Slurm. Yeah, and
like that's
the technical aspect of like getting Slurm working on all the machines in our labs was another thing.
Well, that's actually was going to lead on to my second question, which was what I really want from this is, because at least My problem is I need to run. I would love to use multiple machines to run multiple Gem5 simulations in parallel, but I want guarantees that I'm running in a stable environment across them. I can't just have because at least in my lab, at least in our lab, all machines are slightly different with different packages and things like this, and I don't want that. I want to know that one Gem5 simulation running one machine is got the same environment as it would if it was running on any other. So the question is there a way to kind of neatly wrap like containerization in this? Like I pass it and be a Docker image and it will always spin up in that Docker image regardless of what system it's on and run from there.
Yeah. So at its core, a job is a command and like a CWD. Like the class gem5fs simulation is a wrapper around that to kind of allow higher level description of a job. So you can imagine containerized Gem5 run as a class that kind of spits out the command line necessary to launch Gem5 in a container. Yeah.
I mean, I think, well, yeah. I mean, I'm not sure. Yeah, that's just. I'm not sure if that would require that every machine just has that like the Docker installed and you're just essentially running the sorry, you're just essentially running the Docker command, right?
Yeah.
Okay. Yeah. But that makes sense. I mean, nice if there's a nice clean interface where I specify all my Gem5 requirements and then just say, oh, and use this container for everything or something, or this image. But yeah, that's sufficiently answered my question. Does anyone else have anything?
Cool.
Yeah, it will be good to, as you go through this, it will be good to publish the comparison with Slurm at some point, like, feature-wise, like, what does this offer over Slurm?
Okay, yeah. Thank you.
Yeah, thanks, Mar. Okay, this meeting kind of ended a bit earlier than I thought, but that's okay. I know nothing else in my agenda. So yeah, we have 20 minutes if anyone wants to bring up anything as part of the open mic kind of section. Again, anyone's got anything Gem5 related to speed to bring up for discussion? Nope. Everyone happy? I guess so. Okay. Thank you for everyone for attending. Next one will be looking at the next dev meeting will be the February 12th, I believe, second Thursday of February. Same time. If everyone between then and now wants to have time allocated in these meetings to discuss anything, just let us know. Just say, hey, I want to discuss this PR. Hey, I want to discuss something I've developed. Then let us know. I'll allocate the time. But as always, we tend to wrap up our agenda pretty early in these meetings and have time at the end if anyone just wants to jump in and ask something on the day. Yep. Last chance anyone to jump in and say anything? Nope. Okay. Great. Thanks everyone for attending, and I'll see you all next month. And again, thank you, Mayar, for your presentation. And yeah.
Thank you.
Bye for now, guys.
Bye.
Thank you.